nanohub.org.
Online simulation and more for nanotechnology.
So today we're going to start the first lecture that is a little bit of uncertain quantification. Now originally we're gonna talk about something called generalized linear model. So basically linear regression, extensions of linear regression, the different ways of doing linear regression that answer different kinds of questions. Originally, I had one lecture on this topic where I covered pretty much everything under the sun, but if I did that, then there wouldn't be any time for the handout, so I split the lectures in two. And today we're just gonna work on least squares and maximum likelihood, and basically play a little bit and gain some experience, okay? So it's, I think I will manage to give you more than 30 minutes to do the handout, and it's extremely important that you do it so that you develop a feeling about several concepts that I want to introduce, like underfitting, overfitting, measurement noise, etc. So you'll see. All right, so we start with a reminder. We'll talk about supervised learning. This is just the definition of what supervised learning is. And then we'll talk about regression, which is a particular case of supervised learning. We'll introduce a class of generalized linear models, which is basically a generalization of linear regression models with whom you should all be familiar. I'll show you how you can fit these models by using least squares. And then we'll discuss the problems of least squares, and we'll introduce some maximum likelihood estimates to fix one of these problems. And then there are going to be like 4 or 5 problems that will remain, and we'll see how these can be fixed on Thursday. Okay, but to fix the remaining problems, we need to go Bayesian, and we'll deal with that on Thursday. Anyway, so in the previous lecture, we talked about the principle of insufficient reason. I remind you that you had a set of discrete states that a random variable could take, and if that's all the information you have, then the principle of insufficient reason tells you that you should consider them as equiprobable. Okay, and that was one of the ways we used to pick distributions for random variables. And then we talked about generalizations of the principle of insufficient reason. One of them is the principle of transformation groups, where you say, okay, you want to make everything, you want to pick a distribution that's as uniform as possible as soon as it satisfies the physical invariances, the symmetries of the problem. Okay, so that gives you the principle of transformation groups. And if you are a mathematician, this would make for a very good project. If you're not a mathematician, forget about it. Okay, just do something else. Because it is very involved. The principle of maximum entropy is another thing that we introduced that allows us to pick distributions. And let's briefly talk about it. It depends on the information entropy, which is an invention of Shannon. So Shannon postulated 4 or 5 axioms for an uncertainty functional. A functional takes a distribution and tells you how much uncertainty there is in this distribution. And they're very reasonable, like it should be continuous, the maximum should be attained by the uniform distribution, and so on and so forth. Now, if you use these functionals, you come up with a almost unique representation of the entropy. And it's unique up to a normalization constant that you can pick to be whatever you want, and of course we pick 1. And then once you have a measure of uncertainty, then you can come up with a variational principle that allows you to pick the right distribution. And the variational principle says you should maximize the entropy, you should pick the distribution that corresponds to maximum uncertainty, subject to whatever constraints you have. Okay, and we looked at constraints that are the form of expectations, and we said that with these particular constraints, you can get almost an analytical answer. So you take the entropy, you add the Lagrange multipliers times the constraints, you use the KKT conditions to get equations that will give you the lambdas, the Lagrange multipliers. Okay, that's it. All right. So let's get to the new topic, which is supervised learning. And here's the definition of supervised learning. So you have observations that consist of two types of things, the X's and the Y's. And you can think of the X's as some kind of inputs, and the Y's as some kind of outputs. And the problem in supervised learning is to find the map between X and Y using just these observations. All right? This is pretty much it. Any questions? So the word supervised refers to the fact that you see the outputs, that you have outputs. If you didn't have outputs, if you just had the X's, and you just had to learn something about the X's, like for example the distribution or whatever, then that would be called an unsupervised problem. Okay? Alright, if these Y's are continuous, if they're real values, for example 0.5, 10, 0.25, whatever, real values, then you have a regression problem. If these Y's are labels, like 0, 1, 2, 3, or red, blue, black, bad, good, whatever, then you have a classification problem. Okay? So for the supervised learning, let's say categorization, you have either regression if your outputs are continuous variables, scalars, right? Or vectors, but continuous, then you have a regression problem. If your outputs are labels, then you have a classification problem. Okay? Any questions? So most of the times when we deal with physical systems, we have to solve a regression problem. So we're going to study mostly the regression problem, but you can use similar techniques or variations of what we're going to talk about to solve the classification problem. And it's really the principles that you need to learn about, not the particular methodologies. So we look at generalized models for solving regression problems, but you could use these models and extend them or modify them so that you can actually apply them to classification problems. Classification is a little bit more difficult because it breaks down the linearity of things, and you just get a mathematical problem that is a little bit more involved. But in principle, the principle is exactly the same. Anyway, so we're going to use this data set to introduce these ideas. So this consists of about 200 observations of X's and Y's that are measurements of motorcycle accidents. Actually, they're not real accidents, they are simulated accidents. And what you see in the x-axis is the time after the impact of the motorcycle, let's say with a wall. That would be very hurtful, but anyway. In milliseconds, so how much time has passed after the impact in milliseconds. And on the y-axis, you see the acceleration in g's on a sensor that is on the helmet. Okay, so you see that initially, the first few milliseconds, you don't have an acceleration on the helmet, but then, you're gonna hit something and you'll feel it. Okay? And what we want to do in this problem is find a map between X and Y. Right? So based on that data set. Now this data set is not a simple data set because you see here at the beginning there's nothing going on. And then you have something going on. Alright? And you kind of have a kink here. Right? And what else? At the beginning the noise is very small. But here the noise is bigger, right? So you have an input dependent noise. So it is a heteroscedastic noise, right? So it's a difficult problem actually, even though it is one-dimensional. Okay, none of the techniques that we will introduce today will solve these problems in a satisfactory way. As a matter of fact, we're gonna do better and better up to Thursday, but even on Thursday, none of the techniques that we're gonna do are going to solve this problem in a satisfactory way. And the problem that will remain at the end will be the heteroscedastic noise, which we can solve, and I'll tell you how you can solve it in principle, but we're gonna need Markov chain Monte Carlo to actually solve it, to carry out the necessary computations, let's say. Anyway, so here's the classic regression model. The most general form of a regression model that you can think of is like that. So x is connected to y through a model f of x that has some parameters which I call w. Now this could be any model you like. It could even be a physical model. It could be I set up a bunch of differential equations which I solve and then I grab this quantity. That could be what f does. Okay. So it could really be anything. And most of the principles that I'm going to describe, actually all of them, work for an arbitrary f. So they will also work for whatever your actual physical model is. If you want to calibrate it, they will still work. Okay? But the math will not quite work unless f is linear. Okay? So even though the principles I'm going to state today are general, the least squares, principle of least squares, and principle of maximum entropy are general, you can write them down for an arbitrary f. The way we actually solve these problems will depend on taking a linear f. Okay? So the principles will hold, but if you have an arbitrary f, you're going to have to do a little bit more work than what you see today to finish your fitting, let's say. All right, so the simplest possible model is the linear regression model. All right, where you take each one of basically a constant, right, that you want to fit, and then W1 times the first input that you have, plus W2 times the second input, plus up to X, the D input. All right, it's the simplest possible model you can have. This is not necessarily, this may work when? Well, if your X is, if you're really interested in learning your model at a very narrow region of X, right? Then this will be a good model because you can always go at that narrow region of X and take the Taylor expansion. Okay? And if you make it sufficiently narrow, it will work. Everything is linear if you zoom in. All right? So in principle, you could apply this to any problem you like. But as soon as you start making the region of X a little bit bigger so that you start seeing fluctuations or some variability with respect to the X's, then it will not work. And if this is a physical problem and X is a physical variable and your model is supposed to be invariant with respect to certain transformations of X, this will basically violate almost all the transformations you can think of. Right? So if you tell me X are the locations of, I don't know, a bunch of molecules described in a specific coordinate system, and you want to expand the energy using a linear combination of the Cartesian coordinates of the molecules, you're going to get garbage because this is going to be, your energy is going to depend on the choice of the coordinate system, which is ridiculous, okay? So this is, in general, a very bad choice. Now, a generalization of that is what is known as a generalized linear regression model, okay? Where this looks like the model we had before, but instead of the X, it's linear in the model parameters, right? So the model parameters appear in a linear way, and that's where the linear comes from. Okay, it refers to the fact that the model parameters appear in a linear way. But instead of x, you have a phi of x as the feature or the input. Okay, so it's as if you are taking your output and you are expanding it in a set of basis functions. Okay, and now using these basis functions, you can, if you like, enforce certain invariances or symmetries by making these basis functions satisfy these invariances and symmetries. You can make your output satisfy the same invariances and symmetries. For the example I was talking about before, let's say learning the energy of a molecule, then if you make these phis to be the pairwise distance of all the of each atom from each other atom, so if you use as your basis functions basically the distance matrix, right, and you expand the energy in terms of a sum of the pairwise distances times a coefficient, that will automatically make it invariant with respect to translations and rotations of your coordinate system, and then it's a much better model than the one you had before, okay, which didn't satisfy this invariance. All right, so these phis will depend, I mean, they are, how you pick them depends on what is x really and what is y really and what is the problem we're looking at and what do we know about the problem. Okay, but there are some default choices that you can make. Questions so far? Why are the weights linear? Why did we pick this particular form of so the model is linear in W, right? The model is linear in W, meaning that if you put here W1 plus W2, that will result in YXW1 plus YXW2, because it appears in a linear way. Yeah, convenience. So why the question is, why did we pick the linear a model that is linear in the weights? Well, why should we pick something that's more complicated than that? So if you want to generalize this, right, the first thing you can do is make these guys non-linear, okay, and then worry about the weights later. Yes.
So the functions can be non-linear.
Yes.
Okay. They be combined linearly.
Yes. The functions, the phis, can be anything you want. It could be polynomials, radial-based functions. We'll see some examples later. Any function you want. Okay? But the weights appear in a linear way. So the generalized refers to the phis, okay? And the linear term refers to the weights. All right. So a few of the names that we need to remember. So X is going to be called the input, Y output, or target. So in some books you will see Y as target. The phis, these basis functions, we will call them features. This is the terminology used in machine learning. Okay? Features or basis functions would do. And I'm sure there are other names, but let's just pick two. And the W's, we're going to call them weights or parameters of the model. All right? And of course, to save some writing, I will think of the W as a vector, column vector, and the phi as a column vector, and I will use the dot product of the two. All right? All right, so here's an example of phis. Of course, you can take them to be linear in each one of the input variables that you have, right? So this is one choice. Here's another choice. You can take them to be polynomials, monomials, basically. of the input that you have. And it's good to practice a little bit with this notation that I'm not going to stay on that right now, but this is a useful notation for writing down monomials because it saves writing. So it's called the multi-index notation. If you Google it, you will understand how, I mean, it's ridiculously easy to understand how it works. Okay, you can even understand it from this page, but I'm not going to use this today. I'm just putting it there because I will use it later when I talk about polynomial chaos. And I will explain it later in detail. All right, here's another example of basis functions. These are called radial basis functions. Let me just show you how these look like. So if you draw x, so in one dimension, all right, you pick some centers for the radial basis functions, let's say x1, x2, and x3. And you pick a Gaussian, basically, around with each one of the x's as a center. So here's the first one, that will be phi1. Here's the second one, that will be phi2. Here's the third one, phi3. Okay, and you just expand your output in the set of these base functions, right? Some constant times the red one plus some constant times the green one plus some constant times the yellow one, all right? And of course, in this set of base functions, you can pick the location of the center and you can pick the width of the Gaussian. Okay, so this L controls the width of the Gaussian. L, we picked L for length scale, okay? And of course, you know, if you pick a lot of them with a very small length scale, you can pretty much capture any function you want. And it's a very important base function to remember. All right, here's another one, another choice. You can pick the title is wrong. This is Fourier basis, right? You pick your base functions to be sines or cosines with different periods, right? You sum them all together. So if you like Fourier expansion is included in the generalized linear model, okay, for a specific choice of base functions. And so on and so forth. There's really no limit to what kind of base functions you can pick. All right? So now that we have talked about the generalized linear model and the choice of base functions, let's go to the least squares, which is basically the simplest way to fit a model based on some observations. And it goes like that. We have some data. The data consists of the x's and the y's, instances of x's and corresponding instances of y's. We have our model, which is a generalized linear model, and to fit it, we're going to minimize what is known as the square error. Okay? So you take your model, at each one of the observed points, you take your model and you say, what does my model predict at xi? It predicts y of xi and w, and you subtract from that the actual observation. So you compare the prediction of your model, which is yxi, to the actual observation, which is yi. Okay, so that's the error. You square that, and you sum all the errors up. Now you get the square loss or the square error. Okay. Now if you manage to bring the square error down, you will get the best fit to your model, okay, or the fit that minimizes the square error. But of course, what I want you to realize here is that the formulation of this minimization principle, the principle that to fit your model, you must minimize the square loss, does not depend on the linearity of the model, okay, because here you can put any model you like. Okay, you can calibrate it in this way. But now that we're going to put something linear here, guess what? We're going to be able to do the minimization to carry it out analytically. Okay, that's one of the reasons why we pick the linear models. Any questions? Now, if you ask yourself, why the square laws and not, let's say, the absolute laws, you're absolutely right. I don't have an answer for that. Okay? Why? Because it is convenient. Because it leads to an analytic answer. This principle cannot answer why. Okay? Just because it makes sense. Just because for historical reasons or whatever. Okay? But it's the most common way of fitting models. If you ask why, you're going to get the answer, there's no why. When we talk about Bayesian inference, then you will see why. Okay, but from least squares on its own, it cannot be answered. All right, and that L, we're going to call it a loss function. And of course, if in your problem, it makes sense to take another loss function, perhaps because you're you may be interested, for example, to learn the output in a specific region of the input space. Maybe you don't want to learn it everywhere, okay? So then you may want to concentrate on the square loss on that region, okay? So you may want to change the definition of the loss. Or if you want to learn something else that doesn't depend exactly, I mean, we'll talk about that later, forget about it. But the loss is also your choice. All right, so now if you take a square loss and a generalized linear model, the square loss can be written like that, as the norm of the difference between two vectors, basically, okay? Because your model is going to give you these predictions. Some matrix phi times the weights, and that matrix phi is a special matrix that is called the design matrix. And it is basically a matrix that consists of evaluations of the basis functions on each one of the points you have. So this matrix has as many rows as your observations and as many columns as your basis functions. So if you have n observations and m basis functions, it's going to be n times m. And if you multiply it with the weights, like a common matrix vector multiplication, it's going to give you the predictions of your model on each one of the observations. So that's just a convenient way to write it down. But of course, to understand it and to appreciate it, you're going to have to write it down on your own time. Okay, but trust me, it's going to look like that. Okay. So now we are able to minimize it, right? Because we wrote it as a matrix, as the norm of the difference between a matrix vector product and a vector. We can now just take the derivative with respect to the weights, W, set it equal to 0, and we'll find a unique answer, and that unique answer is given by this expression, okay? Well, phi is that design matrix. It's basically, it has to do with your basis functions. It's phi transpose phi inverse times phi transpose y. Here are your output observations, and this has to do with your basis functions. Now, if you're familiar with least squares for linear regression, in linear regression, you would have here a matrix called X. Okay, it's pretty much the same matrix. Any questions? I'm going to have you prove this for the homework, so don't worry too much about it, okay? It's not a big deal. You just take the derivative. Set it equal to 0. Of course, if you take, this is not sufficient, you need to also take the second derivative and realize that the corresponding matrix that you're going to get is positive definite, okay? Then that will correspond to an actual minimum, and that happens. And you will have to get the chance to do it. But it's so common that I'm sure you're going to be able to find the answer on the web somewhere. So it's not really a homework problem. It's a typing problem. All right. So, a note that I want to make, the problem is like that. This is how you find the coefficients that minimize least squares. You just need to evaluate that expression. And the worst way to evaluate this expression, the worst way is to first build this matrix, then take its inverse, and then multiply it with phi t and y. This is the worst way. Don't do this. Okay? We never take inverses of matrices because it's a very unstable thing to do. Okay? So that's the worst thing to do. We don't do it. Of course, the best way to do it will be to use this, the least square routine of NumPy, okay, which doesn't take matrix inverse. And I'll tell you what it does. Okay, so here's what it does. It takes the QR factorization of the design matrix. QR factorization, linear algebra. Anybody remembers what it is? You do? Well, you should have seen it sometime. So the QR factorization is basically a factorization that takes your matrix and writes it as the product of an orthogonal matrix, Q. So that orthogonal matrix satisfies this property. Q times Q transpose is I. So the transpose of Q is its inverse. And there are very nice and stable ways to find this. And you probably learned these ways in a linear algebra class, not at the graduate, but graduate linear algebra class. And that R is an upper triangular matrix. Okay, it's a matrix that looks like this. It's all zeros here, and it has numbers only in the upper triangular part. Okay? And this is a procedure that you can do quite fast, and it's very stable. And then once you've done it, to find the WLS, the least square weights, you have to solve this linear system. And you see that this linear system, in order to solve it, first you need to multiply y with that orthogonal matrix, big deal, matrix vector multiplication, no problem. And then you have an upper triangular matrix times a vector equals to that, and you have to solve for the vector. But because this is an upper triangular matrix, you can do this very easily. I mean, you can start down there and solve for the last element. Once you find it, you move to the second to last row, and you move upwards. This is called a backward induction. What was that? Here? I'll put a question mark. Maybe. I don't know. I don't remember. We'll see in the next slide where I have the proof. No. It was correct. Okay? So how do you prove this? Well, we just plug in every QR in place of phi, and you see how things simplify. Right? So the answer that we got by taking the derivative was this, and then we just replaced phi for QR. Okay, so that's what we get. And you are right that here, actually, I needed to take t. Absolutely right. So here's a mathematician, statistician. What is your major? Math. Oh, perfect. Attention to detail. Thank you. All right. So, yeah, you get the transpose there. And then you notice that this qt times q, this is I. They're going to annihilate each other. And then you have this. You use the common, this then is going to disappear with that. And then at the end you get that. Okay, that's very simple. All right. So let's put this in practice. Maybe I should go a little bit faster. I'm going too slowly. All right, guys. Let's accelerate a little bit. All right, so I try least squares with a linear basis. You get this. This is ridiculous, all right? So this is a very bad fit. We will say that here we are actually under-fitting the data. Okay? We obviously need more basis functions to describe what's going on. You go to a second order polynomial, you get this. This is also a bad fit. You get to a third order polynomial. This is also doesn't look good. And you start increasing as you start increasing the order of the polynomials, you start, I mean, it looks a little bit better, but you observe strange things here and there, right? So you see that your fit overshoots, and you start having what is called overfitting now. Okay, even though it looks good here, when you go away from the data, you get garbage. And if you go to a degree, to polynomial degree that's higher than 5, you will get complete garbage. All right, let's see what happens with Fourier coefficients, with Fourier bases. Fourier bases, 4 coefficients, 2 sines and 2 cosines. You get this. It looks okay. You increase the number of coefficients. It also looks okay, but it looks like it can be better. Let's double them. We double them. It looks very good. Okay. But why 16? Maybe if we make it 32, it's going to be even better. And you make it 32, and it starts overfitting. Okay. Let's try another basis, radial basis. I'm going to use 5 terms. With 5 terms, I get this. This is very bad. You use 10 terms, it looks better. You use 20 terms, looks good inside, but you do overfit here and there. Okay, so maybe something is wrong there as well. Here's another, just to show you that you can use any basis function you want. I'm going to use step functions now. So these are basis functions that they're just like that. So they're steps. And all I'm choosing is the center of the step. Where does the step happen? So I'm just going to throw a bunch of them, uniformly distributed, and see what I get. Okay? So if I use 5 step functions, I get this. If I use 10 step functions, it looks better. Can use 20 step functions, it looks quite good, I would say. But if you use 40, you start getting garbage. You start getting, you overfit again. And actually, this is a ridiculous number to see. Okay, so there's something seriously going wrong there. All right? Anyway, we'll fix that on Thursday. Yes?
So on the previous slide, it looks pretty good early and then the dip, but when you get into the later part, how do you know that's a good fit when it's all kind of noisy?
It is not a good fit. It is not a good fit. I mean, least square, that's the problem with least squares, that you do not have a way to tell if it is a good fit or not. It's quick and dirty because there's one command in Python that you can use to get this result. So it's very, very easy to do. It's the first thing you should do, but then you should not trust it unless it looks perfect. Then you can probably trust it, okay? But as you said here, you look at this region, it's a ridiculous choice of step functions. It looks good, and then you look here and you say, is this real variation? Perhaps not, okay? Perhaps not. It is basically trying to fit the noise, right? So it's actually overfitting, even in this case. Good question. All right. Issues with least squares. First of all, it cannot quantify the measurement noise, so at no point did we quantify the measurement noise. We didn't know, it doesn't give us a way to pick how many basis functions to use. And if we pick too few, we overfit. If we pick too many, if we pick too few, we underfit. If we pick too many, we overfit. There's a magic number. How do we find them? But we also saw that different choices of basis functions give us different results, and we like to have a way to select the optimal set of basis functions. Least squares doesn't give us that. And it also doesn't give us a way to select the parameters of our basis functions. So for example, the radial basis function, in the radial basis function, you can pick the width. What is the optimal width? Different widths are going to give you different results. There may be a magic number. How do you find it? So we're going to be able to, and there's also one more thing. It cannot quantify the epistemic uncertainty induced by the limited number of observations that you have. So if you did this procedure with 10 observations, you should be more uncertain about what you predict. If you do it with 1,000,000, then you can be very sure about what you predict. How can you quantify this epistemic uncertainty? There's also something that's missing that we're going to do on Thursday. Yes?
Over there, as a start, can we just start with our intuition? Because you were against it. That's how I started.
So you can use your intuition to come up with the basis functions, right? But then you need some hard principles. So to validate your choices. So intuition works very well when you are in 1 dimension or in 2 dimensions. If you have 10 dimensions, it is very hard to apply your intuition. Yes?
Can we combine the functions like step with Fourier or Fourier?
Yeah, of course you can do that. Yes.
And does it give better results?
No. It will overfit. It will, least squares will overfit. If you give it too many base functions, it will overfit. Yes.
For the last point, you said it doesn't give us a way to quantify the epistemic uncertainty.
Mm-hmm.
So when you say uncertainty, can it be represented by you minimize the loss function, but there still will be a minimum loss function. So is that the uncertainty you're talking about?
So here's the problem with the loss function. If you give it enough basis functions, it will go to 0. If you give it n basis functions that are linearly independent, it will match all your data points. It will be exactly 0, and you will have a perfect fit for the data that's completely useless. So the value of the loss function doesn't really say anything, because you also need to take into account the fact that your model may be wrong, one thing, and that your observations may have noise, which is nowhere to be found in this formulation. Okay, so there are a lot of problems. All right. But let's move on, because I think it was a very good idea to split the lecture in 2, because imagine I'm in version 1 of probabilistic regression, and we're actually going to go up to version 7, and all that was in a single lecture. Now we're just going to do version 1, okay? So out of all the problems of least squares, we're going to fix the problem with the measurement noise. So I'll show you how to model the measurement noise, okay? So here we go. We have our generalized linear model, and now we're going to use probability theory for the first time to explicitly model the measurement process. All right, are you with me? So we're going to create a model for the measurement process. And this model is going to be called the likelihood model, or a likelihood function. So the likelihood that you have heard about, I guess, in the past, models the measurement process. It tells you what is the probability of getting the specific y's you have observed at these specific input points if your model is correct. That's what it tells you. Okay? The probability of getting these specific y's at these specific inputs given the weights of your model, let's say. Let's not say the model is correct, given the weights of your model. So, and this is a choice that we're gonna have to make. We're gonna have to choose this probability. The likelihood, okay? It's gonna be a model, basically, yet another model. Of course, we're gonna pick it to be Gaussian, okay? Because it's the most convenient choice. But it could be anything. Questions? I'll probably say it 10 times, so you'll have time to think about it. All right, so what is this quantity going to give us? It's going to tell us how plausible it is to observe these outputs given the inputs and the model parameters. Okay, this is what it is going to be. So in other words, it's going to capture the measurement error. It should model the randomness of the measurement noise, okay, somehow. And it should also model the model discrepancy. So any difference between the actual measurement that is not that is not because of the noise is the model discrepancy. So you should also model that. And in most cases, of course, you will take the measurement error to be Gaussian and the model discrepancy to be 0. Okay? It's because it's very hard to also model the model discrepancy. But this is how you can think about it. Anyway, so if your measurements are independent, so if you are very careful with your measurements so that every time you measure you get an independent measurement, then the likelihood is going to break down like this. So the likelihood of all the data is going to be the product of the likelihood of each observation. Okay? And of course, here is a model for the likelihood of an observation. You can say that it is a Gaussian. Okay, why is it a Gaussian? Maybe because the noise comes from independent, identically distributed random stuff that are added to whatever you measure. Then it's going to be Gaussian. Maybe because you can actually measure the variance of the noise, and then the mean, whatever, it's something that you can also measure. And then the distribution maximize the entropy is the Gaussian. Or maybe because it is convenient, okay? And because you don't have a reason to believe that it is something else. This is also a very good reason. But if you have a reason to believe that it is something else, for example, if your outputs are positive, then the noise cannot possibly be Gaussian. All right? Because Gaussian will give a probability that they're also negative. All right? So you're going to have to transform the noise process. But anyway, this is a simplest choice. So what do we say when we see that? We say that we believe that our measurement is around the model mean, the model prediction. So the model prediction is the mean of the Gaussian. Okay? And it is distributed with, it is contaminated with Gaussian noise with variance sigma square. Okay, and that variance sigma square now becomes an additional parameter to our model. So our model now has, of course, the mean response that comes from the physics or from the theory, and then you have the noise that corresponds to the measurement process. And that sigma is something that you need to estimate as well. All right? So when you have Gaussian likelihood and dependent observations, the likelihood of everything can be written like this, right? It's just the product of all the PDFs of the Gaussians, and this is a multivariate normal with diagonal covariance, which we're going to study later. So, okay, now we have this model that contains both the parametric model and the measurement noise, and we have to pick the parameters. And parameters include both W and sigma. Here's the idea. The idea is to pick the parameters that maximize the likelihood. The parameters that make the observation that we have more likely, okay, if you like, more plausible. All right, this is the simplest idea. This is not the Bayesian way to do. The Bayesian way to do it would be to put priors on W's, come up with the posteriors. We're going to do it next time. But it's a crude approximation to that gives very convenient results. So we'll say that we'll pick the parameters by maximizing the likelihood. Okay? So the likelihood principle is this. And again, I want to point out that the principle can be generalized. The results that I'm going to get from this point on depend on the fact that the model is linear and that the noise is Gaussian. Okay, but the principle is like this and can be generalized. Now it is more convenient, instead of maximizing the likelihood itself, to maximize the logarithm of the likelihood. This is only for numerical reasons, all right? And this is something that you need to keep in mind, because the likelihood may have values of 10 to the minus 6. Or even smaller than that. So you don't want to have to deal with these numbers. Anyway, For generalized linear model, Gaussian likelihood, the log of the likelihood looks like that. And if you pay close attention, what you see here is the square loss. You see the square loss there? So if you maximize the likelihood with respect to W, you are actually maximizing this quantity. If you get rid of this minus sign, you are minimizing this quantity. So you're minimizing the square loss. So here's an explanation for the square loss minimization. It is a good idea to minimize the square loss. I mean, the choice of square loss corresponds to a Gaussian likelihood for your measurement process. So square loss corresponds to Gaussian noise, but you just don't say that you have Gaussian noise. You just hide this fact because you just pulled it out of your butt, okay? But if you are follow a probabilistic approach and you explicitly talk about your measurement process and you make a Gaussian choice, you're gonna get the least squares, the square loss minimization principle. Okay, so the solution you're gonna get is gonna be the same as least squares. So it's gonna have exactly the same problems. Okay, but at least now the choice of the square loss is justified. But there's one more thing that you can get. You can also maximize the likelihood with respect to the measurement noise, okay, which is something that you didn't have with square loss. So now you can say, I'll pick the noise that makes the observations most likely. So you can just add the sigma to your maximization. And for the Gaussian likelihood and generalized linear model, this is the noise you're gonna get. Okay? So this is the best estimate for your noise, is the square loss divided, the average square loss, basically, of your data. Okay, let's look at this noise and see if it makes sense. Oh, I have to talk about predictions. All right, so as soon as you have picked the weights and sigma, you can start making predictions. Question?
So all you're saying is that the samples or the input is coming from a Gaussian distribution.
The input is conditional here everywhere. So the input is given. You can choose it by hand to be whatever you want. It could be a product of chance. But if you look carefully, in all the things that I have been writing down, the input is on the right-hand side of the vertical line. So we're not really interested in saying anything about how the input is distributed. What we said is that given the input, the output you get is Gaussian around your model, okay, centered at your model. But the input, it just conditions everything. So we're not really talking about it. Anyway, so now you go at a new input X and you want to make a prediction. And the only thing you can really use to make the prediction is your likelihood, right? So you say, well, this is my likelihood. If I want to say what Y is at a new X, I just need to use the likelihood, basically. Okay, so you use your measurement, your model for the measurement process, and you put in there the best weights that you have found and the best sigma that you have found, and that's pretty much it. Okay, for the Gaussian, it will look like that, right? So your best prediction is if I measure Y at X, I'm expecting to find it somewhere inside this Gaussian. That's what you're saying, okay? And of course, this is the mean prediction and this is the predictive variance. We'll talk about this in detail later. And you can find like the median of your prediction, which of course here is just the mean. And you can find a lower bound for your prediction. So you can find a line such that the probability of finding an observation below that line is 2.5%. Okay? It's very unlikely to find something below that line. I suggest that you study how I get this. But at the end of the day, that lower quantile is going to be the mean minus 2 times the standard deviation. It's approximately that. Okay? That 2 comes from the cumulative distribution of the Gaussian. And if you're looking for the 2.5 quantile. If you do, you can do the same thing for an upper bound, and the upper bound is going to be plus 2 times the standard deviation. And if you plot it, right, so for the linear prediction, the mean we're getting is this. Lower bound, right there, 2 standard deviations below. The mean is the green line, and 2 standard deviations above is the upper quantile. And let's just see where we start getting with higher polynomials. This polynomial basis, you see how the whole thing changes. I mean, it always covers the data because, you know, that's what it is designed to do, but it still overfits. If we go to a different to a set of basis functions, radial basis functions with 20 terms, I mean, you see that it probably overestimates a little bit the noise, right? So here it looks very good in this region. In this region, it should, we're not really sure if it should be more smooth or if these represent the real fluctuations. And we're gonna put a question mark here, but we can clearly see that the noise is overestimated in this region. That's because, I mean, with our intuition, we can see that the noise in this region is 0, okay? But our model cannot capture that because it has uniform noise everywhere.
Can we somehow extract the noise?
Yeah, but we're gonna have to come up with a principle for that. So to extract the noise, you need to model the noise properly. All right, that's what you need to do. And the question is, how are we gonna model this part of the graph where we have different noise than in this part of the graph, right? So we say that we have input-dependent noise. What do we do with that? That would be something we're gonna do in like lecture 20. All right, again, let me clarify this. This may look ridiculous to you because this is a one-dimensional regression problem, and obviously you can just draw a line by hand, right? And then say the noise here is very small and then becomes bigger. Okay, yes, you can do that, okay? But you cannot do that in higher dimensions. Make sense? Okay, because you cannot even visualize them. So don't be fooled by the simplicity of the problem. All right. With more basis functions, the radial basis functions will still overfit. So we have the same problems. All these problems still remain. How many basis functions should we use? Which basis functions? How do I pick the parameters? How do I quantify epistemic uncertainty? All that next time. Let's play with a handout for 15 minutes. My goal was to play for more, but I mean, I went too slowly. Okay, so